Well, now we're going to take a look at the Gaussian integral, and I've written it on the left-hand side. It's the integral from minus infinity to infinity of e to the minus x squared dx. And I've drawn a picture of it on the right-hand side in blue, and the red hatched regions represent the area under the curve from minus infinity to infinity, and that is the area that we will be computing. So to first solve this integral, we will recognize that the bounds have already been put in place, both the lower bound and the upper bound, meaning that this is a definite integral and it equals a certain value, or we can say a constant. So thus we can set this equal to some constant and we will call that I. So this is equal to the integral from minus infinity to infinity of e to the minus x squared dx. Now if we square both sides, or in other words, we multiply both sides by I, then we will get I squared on the left-hand side, and then we will get an I right here on the left-hand side, on the right-hand side. Now, since I is just a constant, we can bring that inside. I will rewrite that integral sign. There we go, that's better. Negative infinity to infinity of I e minus x squared dx. And now we know that I is just equal to the Gaussian integral. So we can rewrite that as negative infinity to infinity. And inside we have the integral from minus infinity to infinity of e to the minus. Now instead of x squared, we will do y squared dy. And as long as we stay consistent with our variable here, this will be true. So, and then on the outside of this, we have e to the minus x squared, and then dx. Well, we know from properties of definite integrals from multivariable calculus that we can just write this as a double integral. So this will be equal to now the double integral, so minus infinity to infinity, and then the double integral here, minus infinity to infinity of e to the, now we're going to multiply e to the minus y squared by e to the minus x squared, which means we add the exponents. So you get x squared plus y squared, and this is dx dy. Whenever we have an x squared plus y squared, we call that is very conducive to a polar coordinate system. And right now we're in rectangular coordinates, so we're going to want to transfer over to polar coordinates, and we will use the following formula. So x equals r cosine theta, y equals r sine theta, x squared plus y squared equals r squared, and we will solve the Jacobian matrix here. So the Jacobian of r comma theta is equal to, that would be partial x partial r, partial x partial theta, partial y partial r, and partial y partial theta. Now using these two formulas here, we can quickly evaluate, or rather plug in these partial derivatives. So partial x partial r is equal to cosine theta, partial x partial theta is minus r sine theta, partial y partial r is sine theta, and partial y partial theta is r cosine theta. Now if we calculate the determinant of this matrix, then we will get, well, that will be r cosine squared theta, and then minus a negative will be plus r sine theta, or sine squared theta. Now if we pull out this r, we'll get cosine squared plus sine squared theta is just equal to 1, so this equals r. So what we know now is that dx dy is equal not to dr d theta, but rather to r dr d theta. So we've almost converted everything. We've converted the x squared plus y squared. We've converted the dx dy. Now we just need to convert the bounds of integration. Here we have a double integral in rectangle coordinates from negative infinity to infinity and negative infinity to infinity once again, which means that the domain in rectangular coordinates is all values of x comma y such that x is an element of negative infinity to infinity, and y, so I will draw that right here. So y is an element of negative infinity to infinity. And this is just a fancy way of saying R2, meaning you choose any coordinate in the xy plane, and that is the domain that is included in the domain that we are integrating over. Now, how do we convert this into polar coordinates? We'll recall that polar coordinates, instead of having an x and a y, you're going to have a radius, and then you're going to rotate that radius in the counterclockwise direction across a certain angle, theta. So what we're going to do is we're going to say, well, we need to cover every single point in the entire domain. So we're going to choose our radius here, and I will draw it in black. That's going to be an infinite radius. And we are going to rotate or spin that radius in the counterclockwise direction all the way around until it reaches itself. So we are sweeping out this area. So it will be here, and then it will be here, and then it will be there, and all the way around until it matches back up with itself, and we have swept out every single point in the domain, which means that our R, and I will write this in green, so now our new domain, which I will write like D star, this will be R comma theta, and such that R is an element of 0 to infinity. It doesn't need to be negative infinity to infinity, because we're going to sweep it, and theta will be an element of 0 to 2 pi, because there are 2 pi radians in a complete circle. 2 pi radians is equal to 360 degrees. So now that we have our new bounds, and I've written them right here, we can set up our integral in polar coordinates. So that means that I squared is going to be equal to the integral, and I will write our theta bounds first, which means we will be doing them last, so 0 to 2 pi, and then the integral from 0 to infinity of, well, our x squared plus y squared is going to be equal to r squared. So, and then we're going to multiply by an r here, so I'll write that r first, and r e to the minus r squared, and then dr d theta. Now we can apply a u substitution, and we will say u equals minus r squared. Du is equal to minus 2r dr, which means minus 1/2 du is equal to r dr. Now, whenever we change our variables, we have to change our bounds. So u of infinity here would equal minus, and that would be infinity squared, which would equal minus infinity. And then u of 0 would equal, well, that would be minus times 0 squared, which would just equal 0. So now we have I squared is equal to the integral here of 0 to 2 pi, and then that would be times, well, that would be times a minus 1/2, and then the integral from, so our infinity here has turned into a negative infinity, and our 0 has remained a 0, of e to the u du d theta. And notice our r went away because we had our r dr there. Now we have a negative which we can get rid of by flipping the bounds of integration. So I'll rewrite it over here on the left hand side. We have I squared is equal to the integral of 0 to 2 pi, and I'm going to write the 1/2 out front. We will flip the bounds of integration now, so it'll be negative infinity to 0 of e to the u du d theta. This is equal to 1/2 times the integral of 0 to 2 pi. Well, the integral of eu du is eu, and then we will evaluate that from negative infinity to 0 d theta. Well, we know that this is equal to, and we will set up our limit now. So this will be the integral from 0 to 2 pi, and it'll be the limit as b goes to infinity of And now if we plug in our bounds, that would be, and this is b going to negative infinity, rather, of, here, I will just rewrite that entire thing. So this is going to minus infinity of e to the 0 minus e to the b, because this is going to negative infinity. So this will equal 1/2 times the integral from 0 to 2 pi. Well, e to the 0 is 1. And then as b goes to negative infinity, that means you will have a minus e to the minus infinity, which would equal minus 1 over e to the infinity. And the denominator will get infinitely large and the numerator will stay constant, which means that this will converge to 0. So then we will have a minus 0 here, which we don't even need to write, and then we will have a d theta, which means we can actually just write our d theta. So now what this will equal is, this will equal 1/2 theta from 0 to 2 pi, and this will equal 1/2 and then 2 pi minus 0, which is just equal to pi, which is actually a very neat result. Now, we aren't done yet. Recall that we did multiply in the beginning by an I, so this is actually equal to, so pi is actually equal to the Gaussian integral squared, where I squared is equal to pi, and if I is our Gaussian integral, then we would take the square root of both sides, which means that I is equal to the square root of pi, and I will rewrite the entire thing. We have the integral from minus infinity to infinity of e to the minus x squared dx is equal to the square root of pi. It is a very beautiful and satisfying formula, a result in mathematics. It's one of the reasons I love math, and that is the technique for solving the Gaussian integral. I hope you enjoyed. If you have any questions, please let me know. Leave a comment below. I'll be sure to respond quickly. And I will see you in the next video.